Hi, thanks for joining us today. We're going to be talking about exponential functions, reviewing the basic rules and all the stuff you should have learned in your pre-calculus courses about them. Now, the reason we have to review all of this is that this is the chapter where you'll start to learn the calculus of these functions by hand. Prior to this chapter, if you were to see any of these functions in the wild, that would be a signal that you should do something with the calculator. From here on out, it would be fair games to ask you what the derivative of 2 to the x is without the calculator. So to do those problems easier, we're going to start by reviewing all of the rules. First, an exponential function is a function with a constant base and, more importantly, with a variable exponent. We have a constant base and a variable exponent. For instance, 2 is a constant and x is a variable there. E is a constant, even though it's a letter, and x is a variable. 3 is a constant, and using all of these rules, you could show that that is basically just a variable. No big deal. So, these basic properties of exponents will be used when working with exponential functions. Anything to the 0 power is 1. When we multiply the bases, multiplying the same base, you can add the powers. Dividing the same base, you can subtract the powers, not divide the powers. Power to a power, you can multiply the powers. You can distribute powers over multiplication. You can distribute powers over division. And we have rules like a negative power is the reciprocal of a positive power. When you see a negative power, you can move it to the other side of the fraction. Equivalently, if you had a positive power, if you have a negative power on the bottom, that'd be the same as saying a to the positive power. Okay? Negative power would move whatever side of the fraction it's on. We also notice that a plus b to the x power is not a to the x plus b to the x. With numbers, briefly, you have a plus b squared. We all know, you know this is not a squared plus b squared. We have to FOIL this and you get something more complicated. This is never okay. I still catch people doing it, probably out of desperation at this point, but you need to convince yourself that this is not true. It is deadly. Last but not least, please make sure that when you simplify, we do not have negative exponents. No negative exponents when simplifying. No, no, no. All right, so basic examples. 27 to the 4/3 power. The easiest way to go about this is you'll first do 27 to the 1/3 power, and then you'll raise that to the 4th power. 27 to the 1/3 power is the cube root of 27. This is how we define rational exponents when we first get started. The cube root of 27 is 3. 3 to the 4th is 81. Now, you could do 27 to the 4th first, and then have that to the 1/3 power. But 27 to the 4th gets out of control. You can always do whichever order you want. Usually it's best to do the denominator first, the 1/3 first. Just saying. When I teach this in Math 1, a lot of students get bogged down simplifying. Anything to the 0 power though, just 1. Here, a lot of students have the instinct to distribute the power first. I would avoid doing that. I would always make sure I simplify inside first, except in the case where we have a 0 power. So what does that mean? We'll combine the top, e squared over 4, e to the 4th. Same base and they're dividing. The way I would teach this to my Math 1 students is we have the same base, they're dividing, so we're going to subtract the powers. Where will the base end up? The base will end up on the bottom, in this case, because the 4 beats the 2. So we have 1 over e to the 4 minus 2. Now, if you want to just subtract them and get e to the negative 2 and then go to this step, be my guest. And now we'll square the top and square the bottom. Just to go over it in full detail, e squared squared, we're going to multiply the powers. And 1 squared is 1. Not 2, it's 1. And that would be what I would get when I fully simplify it. Again, if you tried this problem out on your own and you got e to the negative 4, I would mark that wrong. If I tried this problem out on my own and I got 3 to the 4th, I would mark it wrong. If it says simplify, you must simplify. All right, go ahead, try this one out. 3, 2, 1. So here we don't really have anything useful. One instinct is certainly to rewrite this without the negative exponent and get 5 cubed over 25 squared. And then some students will then square this out, get 625, cube this and get 125, and then do a division. It's easier to get them to have the same base first. Try for the same bases. So that'd be 5 cubed. That'd be 5 squared. Squared. Once again, we're multiplying the exponents on the bottom. Once again, we're dividing the same base. So we subtract the powers. I'll keep the bigger guy on the bottom. 4 beats 3. And the power will be 1. Okay. Solve 9 to the x equals 27 without using a calculator. Here's the same kind of thing. We're going to try for the same bases. I'm sorry, I don't know how that happened. Try for the same bases. So 9 and 27 can both be expressed as powers of 3. Simplifying that side. And once I have the same base, well, 2 exponentials will only ever equal if the powers are the same. And so x equals 3 over 2. Or 1.5. Okay? Basic. Use a calculator to graph this, and now I'll unveil a new emulator. It's pretty much the same emulator. I don't know why they changed it, but they did. We're going to go to our y equals menu, and we're going to graph those 3 exponential functions. 2 to the x, 2 to the x will be graphed for me in blue. E to the x, which is second ln, right above store. Oh, I did this in the episode. I'm sorry. 5 to the x was next. 5 to the x will be graphed in red. Down one more time, and then second ln e to the x. You can also do second divide to get e, and then caret to the x. That's slow. Here we go. Zoom 6 to make sure we're all looking at the same thing. Well, this emulator is a lot faster. So keep in mind, blue was 2 to the x. Red was 5 to the x. And black was e to the x. So let's notice some similarities here. One similarity I would expect you to have written down. If you haven't had a chance to think about some of the similarities, I would pause the video and try to really think, especially if you're rewatching. Did you pause it? Did you think about it? All right. So one similarity I notice immediately in terms of calculus skills is that they're all increasing. Okay? They all start from almost nothing and blow up really fast. That's increasing, for sure. A pre-calculus thing I might notice is they all have the same y-intercept, which is 0, 1. They're all continuous. Another pre-calculus thing you should notice. They don't have any holes, jumps, or asymptotes. One thing that comes up in class discussions is usually they have the same shape. And if I drill down on that, what do you mean by shape? Well, we might mean they all bend up like that. And that bending upward kind of thing is called concave upwardness. So I think that hits pretty much everything. Oh, I guess you can say they're all always positive. The y-coordinates are all positives. And as we go to the left, they get next to nothing. I think I said already. As we go to the right, they blow up to infinity. So, that's all summarized in this chart. You must memorize this chart if you want to do well in this class. All of these are important facts. Knowing it has a domain of everybody. No problems, no jumps, no asymptotes, no holes. Knowing its range is only positive. It doesn't include 0. Important. What I'm saying is it's important to note e to the x equals 0, never. That's sort of what this sentence is saying. It's impossible for e to the x to equal 0. There is no number that will make this equation work. That's important. The graph of f of x is continuous. Check. Increasing. Check. Concave upward and 1 to 1. 1 to 1, this will come up in lesson 7.3. Horizontal line test. Which means that if I drew a horizontal line at any y value, it only hits each of those guys at most once. X-axis is a horizontal asymptote on the left side only. So the limit as x goes to negative infinity is 0. That's what that sentence means. We have a horizontal asymptote on the left, nothing on the right like that. Y-intercept 0, 1. Another key point is 1, a. F of 1, a to the 1 is a for any number. Okay, last things last. All right, Euler's number, just to get situated. You're going to be asked to do a lot of stuff with E. E is the most common base in calculus, by far. You will see tomorrow, or whenever you watch this next video, functions with base E are much easier to differentiate and integrate. We will do almost everything with exponentials in this course. Here we go. By definition, e is the limit of this expression. You will one day be able to prove that with calculus, but you can just assume that's the definition now. To 3 decimal places, 2.718. That's helpful for a few things, namely sketching a graph. Well, this is exponential. So we know when we have 0, e to the 0 power is 1, because anything to the 0 power is 1. E to the 1 is something like 2.7, so it's way up here. And then we know it has to start off from next to nothing, bend upward, slower than that, I guess, concave up, increasing function, like that. You have to know this by heart. You have to know this by heart. You have to know this by heart, because you'll be asked to do things like use graph adjustments without a calculator. So going step by step, y equals e to the negative x. I'll graph in blue. The exponent is sort of the input here. And when we make the input negative, it does what? Think about it. Pause the video if you want more time. 3, 2, 1. I hope you said it reflects the graph. That's a good first start. It reflects the graph across the y-axis. It trades x's for negative x's. Y-intercepts stay the same. Y-intercepts stay the same. And so now we'd have something that looks more like this. A little less shaky probably, but whatever. So it has the exact reverse behavior, exact reflective behavior. And then we'll graph the function in blue, in red. We'll graph the function in red. What does that plus 1 do? What would that plus 1 do to the blue graph? 3, 2, 1. I hope you said the word shift. More importantly, I hope you said the word shift up by 1. All the y coordinates get added by 1. That shifts up. That shifts up. And it's really important to notice the new horizontal asymptote will be at positive 1. It will be at positive 1 now, because the horizontal asymptote also will shift up 1. Two. Okay? That's it for this lesson. You should try to do all the homework problems. It's a mostly review. Should be a great homework. Should be a good homework. Have fun. Talk to you later. Bye for now.